I like number 95 because it's a nice little thinking problem. You can take a long time on it, or you can actually solve it fairly quickly by just doing it in your head. So we get a 2.51 gram sample of acetylsalicylic acid, and it requires 27.36 milliliters of 0.5106 molar sodium hydroxide for complete reaction. So we've got 2.51 grams of our weak acid. So with a before and after table, we don't know how many moles of that we have, but we do know that it was required that 27.36 milliliters of this at 0.1506 molar was required for a complete reaction, which means afterwards there's none of that. And this should also be 0 after complete reaction. So we can figure out how many moles of sodium hydroxide I have. That many liters. And for every 1 liter, I get 0.506 moles. So I get 0.01397 moles of base, which means that the moles of my acid must also be 0.10397. Okay? So to find the molar mass, I take my grams, which is 2.51 grams, divided by the moles. And I get 179.6 grams per mole. Okay, with 3 sig figs, it'll be 180. Okay? The second part of the question asks you to find the Ka. Well, you can do it the long way, or you can do it mentally. Okay? It says that they added an additional 13.68 milliliters of HCl. So they added 13.68 milliliters of 0.51 HCl molar. Okay? Well, these are really strange numbers. Well, they picked these numbers on purpose. Okay? Because what you can do is mentally think of the acid, the strong acid, think of it as reacting with the base. So instead of adding 27.36 milliliters of 0.5106 molar sodium hydroxide, think of it as adding this much minus however much of the HCl you added. They purposely picked the same concentration because this way you can think of it as just, okay, I didn't add 27.36. What I did is I added whatever this subtraction is. And when you do the subtraction, it also comes out to be a very special number. It comes out to be 13.68. So it's not like, oh, I added this much and then I added this much. It's really like all you did was just add that much. Well, what is so unique about this number 13.368? Well, what's so special about that number is it's half the amount of moles as we added up in this earlier problem. it is half the amount. Okay? So if we're adding half of the amount, we're adding half the number of moles. Okay? So we actually don't even have to really work it out, because if we're adding half the number of moles, we are at halfway to the equivalence point. And at halfway to the equivalence point, the pH is equal to the pKa. And they told us the pH in the problem was 3.48. But just to prove it to you, I feel like I want to do that before and after table. So if we had, so we know beforehand we've got 0.03197 moles, and we're adding 13.68 milliliters of base. So if I'm adding that many milliliters and my concentration is 0.5106 molar, that means I'm going to be adding 0.0, it's going to be half as much, .00698 moles. So then it's going to give me this plus this. So after the reaction, I will have this many moles of my weak acid, 0 of the base, and like I said before, when this number equals this number, when your moles of weak acid equals the moles of the conjugate base, you are at halfway to the equivalence point. And at halfway to the equivalence point, the pH is equal to the pKa. So my pH is 3.48, which means then all I have to do is this. Solve for the Ka, and I get a Ka of 3.31 times 10 to the negative fourth. Like I said, you didn't have to work out a before and after table like I did right here. You could have just jumped right into the recognition that you're at halfway to the equivalence point and the pH is equal to pKa, but I thought I would just prove it to you mathematically anyhow. Okay?